All right, so my name is Ardalan. I'm from Blue Chain Analog Design. I'm the technical chair of the Bunch of Wires PHY working group. And so here we're going to be telling you about some of the work we've been doing towards a 2.1 version of the spec. And you're going to be seeing some of my esteemed colleagues here are also sort of driving various of the sub-efforts. So Kevin in the middle, Kash on the end, and Shahab over here, and I'll let them introduce themselves further as they come on up. So as hopefully everyone who's here in this room is already quite familiar with, we've been working on Bunch of Wires for a number of years now. And it's gained quite a bit of traction and success in the industry as well. And I think really sort of the easiest way to summarize what it is that we're trying to do with Bunch of Wires is really just to create an open PHY and link layer set of specifications that are going to enable die-to-die interfaces to be optimized to their host chiplet products. So obviously, there's a lot of talk about sort of using chiplets, sort of in many different applications, particularly sort of for the desire of doing plug-and-play types of things as well, and that's certainly of interest here too. But kind of a key differentiating feature is that we're not only seeking to enable that, but also seeking to enable people to have a baseline set of specifications they can use for essentially any chiplet product and really innovate and sort of make things adaptable and flexible in the particular areas they need to without essentially sort of throwing out the entire rest of the spec along the way. So for that reason, Bunch of Wires really is architected to be minimalist in the set of required features, but with a large set of options and common approaches that you can adopt, again, to really tailor to the specific end market that you're working on. So the current sort of focus that we have inside of the working group really is on this 2.1 release, where there's essentially 3 spec extensions that we're doing that are specifically trying to enable new and additional types of chiplet products or product categories. So I'm a technical guy at heart, so I'm going to sort of focus on more the technical pieces that each of these extensions is going to end up enabling. We'll tell you a little bit more sort of market-wise and everything in a moment, sort of what it is where these things will be used. But so first of all, if you look at BoW.Optical, obviously this is the intent of enabling optical chiplets of various forms. And here, really, the intention, sort of from a technical perspective, is that we're going to provide a common set of recommended configurations and essentially analysis techniques for how you'd essentially use Bunch of Wires to interface with optical chiplets. Next, we'll talk a little bit about the BoW.Memory. And here, again, from a technical perspective, the main differentiation is really all about allowing dynamic bidirectionality and mixed direction, essentially slices or unit elements, where you can then make use of that for more traditional memory, sort of DRAM types of interfaces, whether in the form of directly chiplets or sort of even embedded into the memory standard itself. And then finally, we'll talk a little bit about the BoW.FlexI. And the idea here is that there's a whole bunch of other applications where either for essentially cost or let's say technology reasons, you may have either a very limited number of wires, you may have actually a very large number of wires available to you, for example, in something like a 3D integrated sort of context. But you really want something that's very, very simplistic, very, very low power, very easy to adopt and sort of enable. And so here we're really focusing on essentially a single data rate, very streamlined PHY, where again you're either looking at sort of very cost-sensitive applications, or for essentially ultra-wide, sort of very, very sort of abundant wire type of situation. So with that, I'm going to just hand over, and these 3 fine gentlemen will tell you more about each of the individual ones.
Thank you a lot. Yeah, first we're going to start with the motivation to have any kind of optical die-to-die interface. I'm showing basically a plot that the top right corner is showing all the optical connectivity, and the green bottom left is where actually right now we are using the electrical. I don't want to go too much to the details, but you see for the distance that get less than 10 centimeters, we are considering co-package and also high bandwidth I/O, as we call it optical I/O. And people are getting actually closer to the GPU and CPU for optical communication. I've seen that the best example of and hot to the news could be Light Matters and others that they are enabling this type of link over optical. But there are so many different ways of doing it in terms of being co-package or near package. I basically, if we look at the left, again, graph here, which I cannot see it from this screen, maybe I have to look here, is the older style was basically leaving the SerDes and retimer all the way at the back of chassis. And then slowly we brought the SerDes and CDR closer to the package, which we call it basically near package optics. And eventually, we are moving the optical engine, as we call it E2O or O2E, inside the package, and it's basically the co-packaged optics as we are talking. Again, at the right side, you see different style of being co-packaged. The optical engine could be single chip, could be, again, multiple chip, and the connection could be over silicon interposer, advanced package, or even organic substrate package that we had. For all this ideas, basically, we were considering and how we can enable bunch of wire to support die-to-die. Then we got to this kind of recommendation. At least for BoW 2.1, we are trying actually to enable bunch of wire over this type of link, where the bunch of wire transmitter is going to communicate to an E2O O2 engine. That E2O or O2 engine is not a retime engine. Then you don't need basically to have a retimer there to save power. And at the receiver, again, a DOM receiver is going to receive it. Again, no timing, just simple equalization and conversion to electrical and pass it to the BoW RX. This is similar to what people are doing it in Ethernet these days, and they call it linear drive or direct drive. Of course, this is an early work. We have to maintain the quality of the link when we pass it to optic and bring it back. Then there's going to be a lot of parameters to consideration, latency of the link, forward clock quality, how much you basically degrade the quality of the clock, quality of the data, how handle the power down, because some people wants to bring down the link or not, and how to address the side channels. For example, if your link requires the basically side channels at the lowest speed, how do you want to handle that? That's the major issue, for example, right now for optical PCIe. I'm going to stop here, and feel free to attend our meeting if you are interested to see where the bunch of wire on optical is going to go.
Great. Okay. My name is Kevin Donnelly. I'm from Eliyan, where you develop die-to-die interfaces. I'm going to talk about a different application area, which is memory. So first, the whole industry, we talked earlier this morning about pushing forward on AI, machine learning, and there's been huge progresses in CPU and GPU and compute engines to drive that. But memory is just not keeping up. And the memory wall, which it gets a lot of press, a lot of people talk about, is one of the limiters on overall system performance. There's been a number of people that have been looking at different ways to talk about using some of the die-to-die and chiplet approaches to drive memory and break the memory wall and improve the bandwidth per millimeter along ASICs. In our working group here, we came up with 3 sort of use cases that we're focused on. The first here is just a discrete memory chiplet, if you will, that talks to third-party memories, such as, let's say, an off-package DDR or LPDDR. And this kind of really is a logic-to-logic interface then. So something like UCIe and bunch wires, as they exist today, can, and in fact, there are already chiplets being built that has this function. So this is a good example application, but it doesn't require any spec changes to do this. So the focus of our group has been on 2 other applications then, from which we're actually making the spec additions that Eli talked about. This example number 2, we're all familiar with HBM, a good discussion earlier. It's one true open market chiplet that ships a lot, but it requires advanced packaging. It's up on an interposer or a bridge. To build an HBM class memory with a die-to-die interface on some kind of standard packaging is a challenge. The bunch of wires type of interface could be applicable to that, but the requirements for the bandwidth that it needs, which is the terabytes per second, 2 terabytes per second of read or write, and the beachfront has to fit in, it's not quite accommodated by BoW as is, and this is one of the areas where we're looking at spec changes. Sort of at the other end of the spectrum, as I mentioned, most memory is off package. You think of your LPDDRs or DDRs chips that are down on the substrate. If you wanted to be able to just pull an LPDDR-like memory up onto a chiplet, you would need a different interface. You don't need a package interface. You need a chiplet interface. And the question is, could we use something like a bunch of wires or UCIe for that? And we're looking at how to apply die-to-die interfaces for this third case, which is more of a direct memory attached co-package as a chiplet. These are much lower bandwidth than the, say, HBM-like case and lower beefront. So I'm going to click down on example 2 and example 3, the 2 use cases, and show the kind of work that we're doing on the spec development. So first on the HBM4, it turns out there's a lot of overhead if you have fixed unidirectional lanes everywhere. You're dedicating a ton of bandwidth for the write side and a ton of bandwidth for the read. Someone pointed out earlier there's applications that are 1,000 to 1 or more of reads versus writes. Why are you dedicating all these write ports if you're not using them, was the question that was asked this morning. Well, we have the answer for that, which is what every other single memory does in the whole world, which is dynamic bidirectional links. You have a single port that can be write or read, because memory, the DRAM itself can't do both at the same time. So by using the links and turning them around, you can get much more higher effective bandwidth per millimeter and much more standard way that it's applicable to memory. It turns out that bunch of wires is uniquely very well positioned to do this. The other thing about memory, memory's not binary. It doesn't want to have an 8-bit or 16-bit interface. It always has ECC and other things on top of it. And a bunch of wires happens to have some additional optional pins that we can repurpose as ECC bits, make a by 18 slice instead of a by 16. And it works quite well for the applications we need here. And so as far as spec additions, because bunch of wires already has bidirectional links available, in its use case, it configures them as either transmit or receive, but we can dynamically transmit and receive using the same interface. We're modifying the spec to allow which previously was not allowed. And we're using the extra bits as ECC and keeping some unidirectional lanes. Memory always has command and address and things like that. And this work is ongoing in the Wednesday 9 a.m. BoW workstream. Also, as a call to action, if you're interested in a standard package like HBM, this kind of work, we're going to be talking about it in that group. In addition, we're looking at the third use case, which I said is just a memory chiplet brought up onto a package. There was a questions earlier about, well, what other kind of memory chiplets are we going to do that aren't this extreme, terabytes per second bandwidth? It is, I think, widely known here in this technical group. Memory chips are built on different processes than logic chips. Memory processes are older technology, slower, and have different optimizations in order to improve the memory bits. All memory interfaces have a very asymmetric nature where the PLL, the timing, all the alignments on the ASIC side, the memory receives the transmitted data and turns around and clocks it back out using the same clock it got for the compute core. Turns out if you look at UCIe or bunch of wires as it exists today, none of the existing die-to-die standards support such a asymmetric, and we're looking then at extensions to do that. And so what we're going to do is taking the BoW spec, which has the transmit data aligned with a clock as you want in one direction, and adding this asymmetric ability to turn it around and have it come back out and make the source side do all the clock alignment to receive that data when it's coming back from the memory. This will make an interface that's very memory friendly and very easy for the industry to adopt to build such memory chiplets. Again, using the FEC and aux pins as ECC, we could do this in a dynamic bidirectional standpoint, but given most of these applications have more limited read to write ratios, and the option we're looking at now is multiplexing command and address data with the write data, so you get a net less write bandwidth, and you have all the read port available all the time for read data. So this is the work we're doing now. This is the spec additions we're doing now. We're doing it in the BoW workstream, and I encourage you to join us if you're interested and want to pursue it further. Okay, I'm going to turn it over to you, Kash.
Thank you. Hi, welcome. I'm Kash Johal, CEO of Yorchip, and I'm going to talk about the flexible interconnect that we're developing together. So there's been a lot of discussion about UCIe and a bunch of wires, and obviously they both fit the high-performance compute marketplace really well. There have been a lot of limitations and questions about cost and the size of the PHYs, et cetera, and BoW.Flexi tries to address that. So compared to a traditional BoW 2.0, we're actually going backwards. We're trying to make it simpler, easier to interoperate, easier to implement in an older node. The world doesn't just operate at 5 nanometer and below. And shocking. And so with BoW.Flexi, you can have 2 bits, 2 lanes. You can have 4 lanes, 6 lanes, 8 lanes, 32 lanes, 68 lanes. So it's meant to be very flexible. We know a lot of applications where things are asymmetrical. Obviously, memory has been mentioned. If you're looking at a video stream, it's usually coming in one direction. An ADC is coming in one direction. A DAC is going in another direction. A lot of communications and applications may be optimized. So we allow you to have use a BoW, but make it asymmetrical. So it's no longer 16 and 16. You can have 16 and 2 or 6 and 2, whatever you want, right? So that's one of the key things. We're going single data rate. So you don't need complex equalization. You don't need extremely expensive clocking, right? It's really running at the core frequency. So if your microcontroller is running at 250 megahertz, there's nothing, you can run the link at 250 megahertz. If your CPU is running at 3.5 gig, you can run the link at 3.5 gig. And the key advantage of that is lower power and latency, right? So instead of a 2 nanosecond latency that everybody is struggling to meet the spec, here if you're running at 3.5 gig, you've got a just like UCI 3D, your latency is half a clock potentially, right? So it's very, very low frequency. Interop becomes really, really simple, right? So there's a lot of advantages. We can support older nodes and mix those with advanced nodes in a seamless way. So that's the basic idea. And the final aspect of this is the ability to support different types of packaging. It may surprise some people in the high-performance compute market that there are actually people still using wire bonding. It is still the cheapest way of assembling die. It won't stop. And there are customers that are interested, for example, in just connecting to die. So if you have an optical die, you can just wire bond to that directly, put your die very close together. You can have a very cost-effective solution, right? So this is the driver for this. And really, we really can build off of BoW as it exists, but just change some of the parameters. So we're still working on that. We invite you to join the committee, which is the same call. So we're doing a lot of innovative stuff at BoW now. We're doing memory, we're doing optical, and we're now making it address a much larger market beyond just HPC and compute. I'll just go over to a final slide of just showing how the bump maps will work. We have obviously clocks in the middle, some framing signals, and then the TX and RX can spread out, right? Whatever you need. And it's very, very straightforward to implement. There is a different version for wire bond because you can only really have 2 lanes, 2 heights, sorry, for staggered pads or single inline. So there'll be a different bump out for that, or pad out for that. So in this simple example, we show at the bottom 6 lanes and 6 lanes. Obviously, it could be 16 and 16 or whatever the customer implements. On the top, we have 6 and 2. So there's 2 TX. And when you flip it over, you see that it connects in the middle, right? So it's a seamless connection, and it should work very easily. So again, we're trying to address and apply BoW to a much broader marketplace. and ease some of the considerations that people have from packaging costs, packaging options, performance, et cetera. So we invite you to join the team. So I think we have some call of action of where to go. That's it. Any questions?
Yeah, no, so that's it in terms of the material we want to put out there. As Kash mentioned, we'd love to invite you all to participate in the working group. BoW is fully openly licensed and available, and everyone's just invited to come and join us and pitch in the great ideas. And if you're interested, there's some links here to go and find some additional information. So thanks all for your attention. We're happy to take any questions.
Excellent work. So one big question, which I think we heard a little bit during the earlier part of the discussion, what are you guys thinking about PlugFest? And right, that's a big industry problem, right?
I'm happy to give my opinion. If you folks want to chime in, feel free. So I think there's a number of fairly significant challenges to really making a PlugFest entirely work. On standard packages, one could perhaps imagine it, but as I think Clint, in the earlier panel pointed out, you're not really plugging something in, right? This is really a design you must do that, a priori you have to sort of, figure out all of the interactions between all the different chiplets you're putting on. So I think it's a little bit early, in my opinion, to really be, sort of going in a PlugFest type of thing. This will be slightly off topic, but that's okay. Where I think things will really start to make a lot more sense is that, again, much like with HBM, there's a defined entire chiplet that is an HBM product. As we define what additional chiplet products are, and specifically the quote-unquote sockets on a package that they plug into, then you can actually viably do something of that nature because you're not redesigning the entire ecosystem each time. You're just saying, no, this is a specific product, and I'm going to do interop of these products. And and then all the other questions become much more obvious.
I'll build on that. I think bunch of wires, BoW as a specification is inherently, intentionally flexible, right? It's a guideline and outline of how to build things. In the BoW.Memory section, we're trying to do the same thing. We're trying to lay down, here's ground rules for two kind of extremes, a very, very high bandwidth HBM-like application and more of a standard memory chiplet directly attached up on the package. But doing interop testing of paper spec, to me, doesn't make a lot of sense. What I envision is these optional ways to build things will be used to build actual product specs. And the place that would be done, for example, is JEDEC, if it's a memory. And JEDEC would define a memory chiplet with a certain interface. There are no PlugFests for HBM, right? I mean, the concept doesn't exist. You're not randomly plugging stuff in. There's purpose-built ASICs talking to purpose-built memory. The memory has a very detailed spec. There is no ASIC spec for any memory ever. The memory guys are supposed to design their chips to talk to the memory, which is incredibly detailed, like hundreds of pages in the specs, right? And that isn't the purpose of BoW, is to go to that level of prescription. So I think a BoW PlugFest, I'm not sure that makes sense, but end product PlugFest for a specific socket. And it could be an IO SerDes chiplet, like I was talking about earlier. That could be a socket, right? Could be a memory, like I'm talking about. At that level, then yeah, interoperability is really critical. Anyways, my opinion.
I have a completely different opinion. Awesome. just to be different and see if anybody's awake. I agree with everything that's been said so far, by the way. But I do think that it is something that the customers are really interested in. And one of the things that we've been are sort of thinking about working on is sort of an FPGA, which has, let's say, a BoW and a UCI interface. So it at least becomes a platform for somebody to plug in their device. Because right now, if you develop a chiplet, you have nothing to connect to. But at least if you can connect it to an FPGA block that can exercise it, and then customers can compare different things, that starts to become interesting. So, but a plug fest in the classic case where you have a plug and you plug something in and then plug it out and plug something else in, I think frankly, it's not going to happen, right?
You came back to agreeing with us.
I just want to add to it that on top of all things that you mentioned, I think we should not forget power too. You know, as soon as we get to the plug, then the RF loss and extra power that we have to bear.
I think there was a question pending in the back, perhaps? No? No. Or maybe I forced one.
Good morning, guys. Quick question. So I guess this is more like an open source way to do hardware, and at a high level, in this room, I guess on the panel, there's no big memory guys or big vendors on the panel. So, and I'm from a small company, so obviously I'd like to spur this innovation. But my question is, how do we convince the big guys like a Samsung or SK Hynix or whoever to want to do this type of thing?
Well, on the memory part, I'll just speak to that. So they're very interested and highly involved in all memory product spec definitions. That just doesn't happen at OCP. That happens at JEDEC. So they are actively looking and talking about how they can build products that use die-to-die interfaces. And what I want to do is make a UCIe as part of the conversation. I want to make sure a bunch of wires is part of the conversation. I'll also say that JEDEC and OCP have a pretty strong collaboration and have done joint work together already. So I think that's a good direction.
Yeah, and I was going to follow up on that. I think if you go and you check out sort of the specs that were published, you'll see some larger names than are represented here in this particular panel at the moment. And I think the other point that Kevin was touching on is, yeah, I think these things will become much more, let's say, apparent, sort of which players would want to be investing in them. I think, once you're indeed really talking about a chiplet product spec, right? Because that's where sort of the rubber really meets the road in terms of, these concrete definitions, the hundreds and thousands of pages of saying, yeah, like, what is this chiplet? How am I going to be using it? What are the end markets that's actually going to be sold into? And, that's where obviously the real dollars comes in.
But thanks.
All right. Thank you very much, everybody.
Thank you.